Welcome everyone. Today we're going to talk about eigenvectors of matrices as a prelude to learning about the anisotropic or the fully general version of the multivariate normal distribution. Also, eigenvectors are going to come up again later in the semester when we discuss principal components analysis and when we discuss spectral graph partitioning. So we want to understand eigenvectors quite well. It's worth the trouble to learn how to visualize them and understand them. When I was an undergraduate student, the teaching of linear algebra was pretty bad, and I came away from my first linear algebra course knowing how to do the problems, but not really having any intuitive understanding of what it really meant. And I hope that Berkeley teaches you better, or wherever you came from and took your first linear algebra course teaches you better. But just in case not, I'm going to start with a review. And I'm going to begin with the definition of an eigenvector is something you all should remember. If you're given a square matrix called A, then if there is a non-zero vector such that A times V is equal to lambda V for some scalar value lambda, then V is said to be an eigenvector of the matrix A. And it has an associated eigenvalue, lambda. That is associated with the eigenvector V. So, okay, that's the definition, but what does it mean? Intuitively, it means that V is a magical vector that, after being multiplied by A, still points in the same direction, or the opposite direction, which is minus the same direction, but we consider that essentially the same direction. So let's look at a couple of examples. Consider an eigenvector that has an eigenvalue of 2. So what I'm going to do is I'm going to draw a coordinate system 4 times. And we're going to go from left to right and apply the matrix A to a vector V over and over again. And so suppose, for instance, that this vector here is an eigenvector. So V is an eigenvector with eigenvalue 2. What that means is that when we multiply A by V, we get another vector that points in the same direction, but it's twice as long. And we can repeat this process. So if we multiply it by A a second time, then it's twice as long again, 4 times as long as V was. And you can do that a third time, and so on. So every time we multiply it by A, it gets twice as long. A contrasting example, let's suppose that we have an eigenvector with an eigenvalue of -1/2. Again, I'm going to draw four consecutive vectors, all based on an eigenvector with eigenvalue -1/2. And so let's start with a vector W that points in this direction. And suppose that that is an eigenvector of A with eigenvalue -1/2. By the way, notice that W is orthogonal to V. Symmetric matrices, their eigenvectors are orthogonal to each other. So when we multiply this vector by A, it gets cut down to half its original size. And because the eigenvalue is negative, AW points in the opposite direction of W. And we can repeat that process again. So we get A squared W here. We get a cubed w here, which is 1/8 the length of w, and pointing in the opposite direction. So the thing to understand is that for the vast majority of matrices, most vectors do not have this property. Most vectors, you apply a matrix and now it's pointing in a different direction. To be pointing in the same direction makes a vector special. And we can often understand what linear transformations do by looking at their eigenvectors and eigenvalues, which are the special vectors whose directions do not change when you apply A. Now, as you see here, when you scale an eigenvector, it's still an eigenvector. Only the direction matters, not the length. And so let's look at a few consequences, mathematical descriptions of what we've just observed here. So first of all, if V is an eigenvector of a matrix A with eigenvalue lambda, then what about A squared or A cubed or A to the fourth? As we've just seen, V is an eigenvector of those matrices too. So in general, it's an eigenvector of a matrix A to the K for any positive integer K. And the eigenvalue is going to be lambda to the power of K, because every time we apply A once, we're scaling the eigenvector by lambda. And you know the way that you would prove this, for instance, if you start with A squared of V, you can write that as A times AV, and by definition, AV is lambda V. Then swap those two around. You've got lambda squared V. And so then if you want to do A cubed V, you have one extra step where now we multiply it by A again, and we get another lambda, and so forth. Another observation that we want to make about eigenvectors applies when A is an invertible matrix, only when A is an invertible matrix. In that case, V is also an eigenvector of A inverse. And what is the eigenvalue associated with that eigenvector for A inverse? Well, it's lambda inverse. And this is because A inverse V, well, if we just take the V and we look at the equation AV equals lambda V, we can rewrite that as V equals 1 over lambda AV. And then we just leave the lambda behind. So one way to think about the intuition for this is to go back to the figures up above, but instead of going from left to right, now imagine going from right to left. Every time you apply A inverse, this is what we're doing. All right, so to say it simply, when you invert a matrix, the eigenvectors don't change, but the eigenvalues get inverted. When you square a matrix, the eigenvectors don't change, but the eigenvalues get squared. Now, these theorems are pretty obvious. The next theorem is not obvious at all, but hopefully this is a theorem that you've seen in your linear algebra class. It's one of the amazing things that make symmetric real matrices so special. It's called the spectral theorem. Every real symmetric n by n matrix has real eigenvalues. Never complex is what I'm saying here. And it has at least n eigenvectors that are mutually orthogonal to each other. And what I mean by that is that if vi is one eigenvector of A and Vj is a different eigenvector, then their inner product is going to be 0 as long as I is different from J. And this spectral theorem takes about a page of math to prove, so it's not as simple as the other ones. So we won't do that proof here. One important minor detail is that a matrix can have more than n eigenvectors. It can have more than n directions that have this magic property. Because if two eigenvectors happen to have the same eigenvalue, then any linear combination of those two eigenvectors is also an eigenvector. And so if you imagine two eigenvectors with eigenvalue 3, then the whole plane spanned by those two eigenvectors, all the vectors in that plane, not counting 0, are eigenvectors with eigenvalue 3. So when that happens, we just arbitrarily pick two vectors in that plane that are orthogonal to each other. That way we get what we desire, which is we want to get n eigenvectors that are mutually orthogonal, and that set always exists. Even if there's an infinite number of eigenvectors, we want that finite set that is mutually orthogonal. And the great thing about that is that we can use them as a basis for our feature space, or in this case for Rn, if we're talking about an n by n matrix. And that's going to give us power to analyze a wide variety of different phenomena in machine learning and elsewhere. Someone asks why it's called the spectral theorem. I am actually not sure about that. Kevin, do you know?
I didn't, but I just searched it up, and apparently it has something to do with physics and how physicists did something related to spectral lines. I'll send a link in the Q&A.
Okay, cool. Thank you. It's a good question. I should learn that. So I want to talk about a way to visualize symmetric matrices so that we can gain some intuition about what a matrix means, what its linear transformations mean. And one of my favorite ways to visualize a symmetric matrix is called the quadratic form. And it gives us hints about how applying the matrix affects the length of a vector. So what I'm going to do is I'm going to show you some images with let's compare two different functions. That the first one is just the function z squared, meaning you've got some vector in space z, and if we plot z squared, we're just going to get a nice paraboloid. I'll show you in a second. Another way to think of that is z transpose z. A second thing we're going to look at is, okay, what happens if we insert a matrix in there? And for reasons that will become clear later on, I'm going to use A inverse as the matrix that I'm going to stick in here. And I'm going to ask, what does the function A inverse x all squared look like? And another way to write that, by the way, is x transpose A to the minus 2x. We're going to compare these functions, and we're going to use eigenvectors as a way to sort of morph the shape of the first function into the shape of the second function. So that's why we want to consider those two functions. And the first function is quadratic, and it's isotropic. And what I mean by that is that the uh, curvature is the same in every direction. And if you draw the isosurfaces of this function, you get spheres, like perfect spheres, not ellipses or ellipsoids, but perfect spheres. The second function, on the other hand, so first of all, this is called a quadratic form. And in this case, it's the quadratic form of the matrix A to the minus 2. Assuming again that A is symmetric. And this function is not isotropic in general, unless A just happens to be some multiple of the identity matrix. And so that means that when we look at its isosurfaces, they're going to be stretched out. They're not going to be perfectly spherical. They're going to be ellipsoids. So let's take a look at some of these. All right, so again, on the left, we have the function z squared, and I've drawn it two different ways. So at the top, you can see a 3D plot. We've got z1 on one axis, z2 on another axis, and then the vertical axis is z squared. On the bottom, we have a contour plot where, as usual, the features z1 and z2 are what's graphed, and then the function value, we look at its isocontours. Same thing's happening on the right, so I won't draw those axes again, but the function on the right is a to the minus 1 x squared. And the way I want you to think about this is, there's a specific a. This is not just for any a. I'm showing you this for a very specific a. And the reason why I chose this A is because it has exactly the eigenvectors and the eigenvalues that I was graphing at the very beginning of this lecture. So one eigenvalue of 2 and one eigenvalue of minus 1/2. And we want to think of the graphs on the left as being in Z space and the ones on the right as being in X space, where there's a transformation X equals A times Z. So if you have this identity X equals A times Z, then in essence, these two graphs are both graphs of the same function, sort of, except in a different space in each case. So we have an affine transformation from one space to the other, but we're mapping the same quadratic in both spaces, just before and after that affine transformation. Now, let's look at where our eigenvectors are. So the eigenvectors of A, again, are, there's there's V1. So that eigenvector, it's not a coincidence that it matches the long axis of that ellipse. And this is the one where lambda1 is 2. And then in the other direction, we've got a second eigenvector. And this is the one whose eigenvalue is -1/2. And so one way to think about this is that we started off with unit vectors pointing in the same direction as v1 and v2. And when we apply a to those vectors, well, this unit vector gets mapped to a vector that's twice as long, just like I showed you before. And the vector on the left gets mapped. Oh, I guess I need to fix one thing here. I should have started with this in the opposite direction, because that's -1/2. So the bottom vector gets multiplied by -1/2, and that takes us to the vector right there. So when the way that A maps a vector, that applies to any particular point on these isocontours. So we have a particular point that has a particular f value, and that gets mapped to a corresponding point using the eigenvalue as a multiplier, as I showed you. And the vertical values of those two black points are going to be the same because because the one on the right, if you set x equals az, then these two functions are, of course, the same. They're equal to each other. So in general, you can think of the matrix A as mapping the circles on the left to the ellipses on the right. So if you look at this inner unit circle, and you take all the points on that circle, and one by one, you map each one of those points through A, then that's going to give you this set of points on the right. That's what A does. It turns circles into ellipses according to the eigenvalues and eigenvectors that we've chosen. And therefore, those eigenvectors become the axes of this ellipse or ellipsoid, and the eigenvalues become the radii along each of those axes if you started with a unit circle. Let's try to verify that. So what I'm claiming is that if we draw the function, or if we draw the function or the contour plot of a to the -1 x squared, and we look at its isocontour with iso value 1, then that is the equation of an ellipsoid. With its axes being the eigenvectors, and the radii along each of those axes being the eigenvalues. And why is that true? Because if you pick an arbitrary eigenvector vi, and since eigenvectors can be any length, let's choose the vi's to have length 1 so that they're unit vectors. And then you set A inverse x equal to that eigenvector, that unit eigenvector. Well, that means that vi lies on the unit circle. And it means that x is equal to AVI. And so since VI is an eigenvector with eigenvalue lambda I, this AVI, or x, is going to have length lambda I, which means that AVI lies on that ellipsoid that I'm claiming that it lies on. So hey, Kevin, are there any questions about that?
Yeah, there's some confusion about what the graph on the right-hand side represents. I'm not sure if you were able to clarify it for those people,
Oh,
but maybe if you can like label the axes for the
okay.
right plot, just like you did for the left one.
You're right. I should have done that because they're not the same, of course. On the right, we are plotting, well, the function that we're plotting is this function here as a function of x. So pardon me, I should have made that more explicit. And so the axes here are x1 and x2. The vertical axis is, we apply A inverse to those two features, x1 and x2, and we square it. Yeah, apologies. I shouldn't have tried to shortcut that. Other questions?
Yeah, let's see. Yeah, I'm trying to see which of these is worth answering right now.
I see someone asked what is an affine transformation, and here it just means a linear transformation. But it also, I think of it as taking something and stretching it in certain directions and shrinking it in other directions, which is what we're doing right here, is when you take, say, this direction here, and you stretch it to be twice as long, that's part of what affine transformations can do. See?
There's one question asking about like why you wrote like x equals az when you drew that arrow from the left plot to the right, but then we're plotting the norm of a inverse x squared.
Well, I don't know if I understand the question. I'm fixing x and z to have this relationship with each other. And so this is just imposed by fiat, and pointing out that once you set x equal to az, then the function z squared and the function a inverse x squared are now the same function. So, but they look different because we're plotting one of them in terms of z and one of them in terms of x. If you plotted them both in terms of z, they'd be exactly the same function, this one here. If you plotted them both in terms of x, they'd be exactly the same function, this one here. But it's nice to get one plot in z space and a different plot in x space, though we're still thinking of them as being the same function as long as with respect to x, for instance, or with respect to z. So I'm imposing this relationship so that, which you can think of as a change of variables, like you probably did changes of variables in calculus, in multivariate calculus class. So think of this as x and z are two different variables representing the same system.
Okay, I think that's all the questions for now. I can take care of the rest in chat.
Okay. I do see someone asked, what if lambda isn't positive? And so, of course, if you have a negative eigenvalue there, the length of the vector, I mean, by definition, length is still positive, but the vector has changed directions. However, when you're going from a circle to an ellipsoid, it doesn't really matter if some of the vectors change directions. You're still going to get the same ellipsoid either way. A special case that comes up sometimes is, of course, the case where A is diagonal. So if A is a diagonal matrix, that means that the eigenvectors will be the coordinate axes. And so that's a special case where your stretching and shrinking directions are all nicely lined up with the coordinate system. And so we can say that the ellipsoids are axis aligned. And by that, I mean, when you have a diagonal matrix, you can get an ellipse like this. You cannot get an ellipse like this, because that's not axis aligned. All right, so let me remind you some definitions that you're all already familiar with, but let's think about a general symmetric matrix M. So M is said to be positive definite. If W transpose MW is always 0 for all non-zero values of the vector W. And that is equivalent to having all the eigenvalues positive. Our symmetric real matrix is positive semi-definite. Which is a slightly weaker condition. All it requires is that W transpose MW is greater than or equal to 0 for all the vectors W, or equivalently, no eigenvalues are negative. And we say that a symmetric matrix is indefinite if it has at least one positive eigenvalue and at least one negative eigenvalue. And of course, one property of symmetric matrices is that they're invertible if none of the eigenvalues is 0. Or to put it another way, they're not singular. And of course, this is something we always like to see visually. So let's put together some examples of these. So what we've got on the left is a positive definite matrix. Which you'll notice by the fact that it's curving up, smiling in every direction. In the middle, we have a positive semi-definite quadratic form. And this quadratic form, well, doesn't look all that different from the positive definite one, but there is a trough running down the center here where the vertical value, or W transpose MW, is the same everywhere on that line. So there isn't just one minimum, there's a whole line of minima in this example. In general examples, there could be a whole subspace of minima. And so that is positive semi-definite, but it's not positive definite because one of the eigenvalues is 0, corresponding to the eigenvector that points in the direction of this line. And on the right, we have an example of an indefinite matrix, or the quadratic form of an indefinite matrix. And so you can see that it looks like a saddle. It's curved up in one direction and curved down in a different direction. So there's an eigenvector with positive eigenvalue in the curve up direction. There's an eigenvector with negative eigenvalue in the curve down direction. The eigenvectors don't really curve like that, but you get the idea. And in the left example, by the way, you can kind of eyeball the eigenvectors as well, because clearly there's a direction where we go uphill quite steeply, and there's a different direction orthogonal to that where we go uphill much more gently. And in the positive semi-definite case, there's an eigenvector also going up steeply, or that's orthogonal to the trough eigenvector. So I cast this in terms of a general matrix M, but the specific matrix that we were looking at, because it's going to be important to us when we look at the multivariate Gaussian distribution, was x transpose a to the minus 2x. So just set m equal to a to the minus 2 here for our purposes. So first of all, because there's a square here, a inverse is getting squared, this matrix a to the minus 2 is always going to be positive semi-definite. It can't have a negative eigenvalue because we've squared it. Now, if m is positive definite, then when we look at the contour plot of m's quadratic, oh wait, I'm jumping ahead, sorry. All right, so I should also say, since A is invertible in the situations that we're going to be looking at, meaning the anisotropic multivariate normal distribution, there can't be a 0 eigenvalue either, because if there was a 0 eigenvalue, A would not be invertible. And so we're always going to be in a situation where we have an invertible matrix there. And so we're not even going to have a positive semi-definite a to the minus 2. We're always going to have a positive definite a to the minus 2. All right, so that's how m and a to the minus 2 are related. Basically, think of them as the same matrix, but this is a special case where we are using this matrix a to the minus 2. And so given that we know that for the distribution that we're going to be studying, this is going to be a positive definite matrix. What can we say about the isosurfaces of x transpose mx, or x transpose a to the minus 2 mx? Well, the contour plot, of course, of m's quadratic form, will have ellipsoidal isosurfaces whose radii are determined by the eigenvalues of m to the minus 1/2. So like if we're in this situation where we're setting m equal to a to the minus 2 for some matrix A. We can flip that around if someone gives us a matrix M and we want to understand its isocontours, then it's really this matrix A is what gives us a clear understanding of those isocontours that tells us the axes and the radii of the ellipses. So we can set A equal to m to the minus 1/2 if somebody's giving us a matrix M, which is what usually does happen when you use the multivariate normal distribution. And so the eigenvalues of m to the minus 1/2 are the inverse square roots of the eigenvalues of m itself. And that's something you need to remember when we're trying to define Gaussian distributions. I will mention that in the special case where you only have a positive semi-definite M instead of a positive definite M, the isosurfaces aren't generally ellipsoids anymore. Instead, you can think of them as being cylinders, because some of the dimensions, the isocontour goes off to infinity instead of eventually looping around like an ellipsoid. So the isocontours in general are usually ellipsoids, but if you have a zero eigenvalue, they could be cylinders. If you have an indefinite matrix, then you have hyperboloids. Any questions about this?
Yeah, one of the questions was what happens if one of the eigenvalues is 0? I think you just answered it, but if it's still confusing, can you message in the chat anyone who asked that question?
Yeah, I hope I just answered it. I can't think of anything else to say immediately, but well, someone asked if I can draw an example of a cylinder isosurface, and I mean, in a sense, this really is one. It's better, of course, to do it on top of the contour plot. I don't know if I can do a great contour plot diagram right now, but it would look something like, yeah. So the contour plot would look something like this, where you know, the trough of the paraboloid is here, and instead of getting the ellipsoids you would normally expect to get, those ellipsoids have straightened themselves out in some directions. Now, it's hard to, the reason I call them cylinders is there could be many dimensions in which they're still round and many other dimensions in which they're perfectly straight. It's a little hard to visualize that when you only can draw a two-dimensional diagram. So sorry about that. Someone asked if we can explain the square root matrix m to the minus 1/2 again. The reason why we're doing that is typically what's going to happen is somebody's going to give you a quadratic form that looks like this. They specify a matrix M and say, hey, X transpose MX is what you need. Or actually it's going to get a little more complicated in the anisotropic normal distribution. It's going to look like this, where you have a matrix sigma to the minus 1. But the matrix that actually is the simplest one for understanding the eigenvectors and eigenvalues and what your isocontours are going to look like is this matrix A, where you have an a to the minus 2 between the x's. If you have that, then A tells you the geometric intuition that we're looking for. And so what you do is you set M equal to a to the minus 2. And the solution to that is A equals m to the minus 1/2. Or in the case of the anisotropic normal distribution, you want to set sigma to the -1 equal to a to the -2. And the solution to that is a equals sigma to the 1/2. We'll see more of that later. So I don't want to dwell on it too much yet. But the idea is someone gives you an m, or someone gives you a sigma, and you want to know from that, what is the a that's going to give you the intuition about what those isocontours look like. And it's the eigenvalues of a that will be the radii of the ellipses. That's why we care, of the ellipsoids. So in order to build intuition about these eigendecompositions, about how we go from a matrix to eigenvalues and eigenvectors, I actually think that for when you're trying to learn, when you're trying to understand this stuff for the first time, it's easier to go in the opposite direction. So in practice, there are a lot of applications where you're given a matrix and you want to extract its eigenvectors and eigenvalues. But for the purposes of learning this stuff for the first time, I think it's easier if you start. Imagine you have a set of eigenvectors and eigenvalues, and you want to construct a matrix that has those eigenvectors and eigenvalues. So maybe you have a particular ellipsoid in mind. You want an ellipsoid with certain axes and certain radii along each of those axes. So you specify those numbers. Now, can you build a matrix that will actually give you those eigenvectors and eigenvalues? So yeah, you can, and it's actually a lot easier than going the other way around. So let's do it. We're going to choose n mutually orthogonal vectors. And let me emphasize that these need to be unit vectors for the math that I'm about to do. Each vector is of length n. So we're going to break with convention. Here, the subscripts are not addressing individual components of a vector. Rather, this is a list of n vectors. So v1 is a vector, vn is a vector, and everything in between is a vector, an eigenvector that we want to have for a matrix. And they have to be mutually orthogonal because we want them to specify an orthonormal coordinate system. Then once we've chosen our vectors, we're going to collect them together in a matrix that we'll call capital V, whose columns are the eigenvectors. So just put them all together, side by side, column by column, into an n by n matrix. And we call that V, capital V. And the first thing I want you to observe here is that once you've chosen those vectors to satisfy those properties, then V transpose V is going to be I. Why is this true? Well, think about the off diagonals first. The off diagonals of the identity matrix are 0. That's saying that any two different vectors, Vi and Vj, their inner product has to be 0. They're mutually orthogonal. And then think of the diagonal entries of I, which are all 1. That's saying V transpose V equals I means that each of those V's is a unit vector. When you multiply it by itself, you get 1. Once you know that V transpose V equals I, that tells us that V transpose must be the inverse of V, because there's only one matrix that you can multiply by V and get the identity matrix, and that's V inverse. And once you know that, well, then if you know that V inverse V is the identity matrix and V inverse is also the identity matrix. So since V inverse is V transpose, that tells us that VV transpose is the identity matrix as well. Now, any matrix V that is constructed this way is called an orthonormal matrix. Also sometimes called an orthogonal matrix. I like the term orthonormal because it really stresses that these are unit vectors, but orthonormal or orthogonal implies that all the vectors are mutually orthogonal to each other. and so are the rows for that matter, it turns out. And when you apply such a matrix to a set of vectors, it acts like a rotation. Sometimes they're called rotation matrices because they essentially take all the points in your coordinate system and just rotate them around some axis. Or sometimes they're not rotations, sometimes they're called reflections, which means you take the mirror image around some hyperplane. Rotations and reflections are almost the same thing, but a rotation is what you get if V has a determinant of +1. A reflection is what you get if it has a determinant of -1. All right, so we've chosen our eigenvectors. Now I want to choose our eigenvalues. Or if you're thinking in terms of building an ellipsoid, you want to build a quadratic form whose isocontours are ellipsoids with certain axes and certain radii. Let's choose those radii. And so those are going to be the lambda i's, our eigenvalues. So there's a nice way to encode this, which is we're going to have a big diagonal matrix called capital lambda, whose diagonal entries are all the little lambdas. And since it's a diagonal matrix, all the off diagonals are 0. And recall that the definition of an eigenvector, as I said at the beginning of this lecture, well, what I said at the beginning is that it's a vector v such that AV equals lambda v. We're going to write that now in a matrix form. We're going to write it as A times the matrix V is equal to the matrix V times this capital lambda diagonal matrix. And so that's essentially just another way of writing this, is that the original definition, AV equals lambda V, now we're just applying it to all of the eigenvectors at once instead of doing one eigenvector at a time. So this AV equals V lambda is by definition. It's just our original definition of eigenvector written out all the eigenvectors in one shot. And so once you've got this way of writing it, notice that if you post multiply both of these by V transpose, then those must still be equal. And so that leads us to a very important theorem. If you define this matrix, V capital lambda, V transpose, to be a matrix, or sorry, wrong. If you notice that VV transpose, we already said that that's just the identity matrix. That cancels out. So we can shorten this to just A on the left-hand side. And then we have that if you define your matrix A to be V times capital lambda times V transpose, then that has the eigenvectors and eigenvalues that we have chosen. And let me write this another way as well. I think it's useful to notice that the matrix A can be expressed as a sum over all the eigenvectors, where for each eigenvector, you add in lambda I times VI transpose. And this VI transpose, you'll notice that that is not an inner product. It's not VI transpose VI, it's VI transpose. And there's a name for that. It's called an outer product matrix. And it's an outer product because instead of collapsing two vectors down to a scalar like you do with an inner product, you're actually blowing it up into an n by n matrix. So you're multiplying one vector of length n by another vector of length n, and you get this big n by n matrix, which only has rank of 1. So again, this is a nice way to express any matrix A as a sum where each eigenvector is contributing one term to the sum. And by summing them up this way, you're going to get a matrix that has exactly the eigenvectors and eigenvalues that you asked for. Now, what we've just written here, is called a matrix factorization. Because we factored A into 3 different matrices. But there are lots of matrix factorizations. This is a particular matrix factorization called the eigendecomposition. And again, we're not going to prove it, but every real symmetric matrix has an eigendecomposition like this. Also, we think of capital lambda as being a diagonalized version of A. In a sense, it's kind of doing the same stretching and shrinking that A does, but in a different coordinate system. And since lambda is diagonal, it exposes exactly how much it is shrinking or stretching each direction along the diagonal of lambda. And so that's the information you get when you compute the eigendecomposition is in what directions are you stretching and shrinking things, and by how much, by what factor. And so when you think of it that way, you can think of V transpose as something that rotates the ellipsoid to be axis aligned. And so when I think about applying a matrix A to a vector, let's think of a vector Z. Well, the eigendecomposition tells me that I can think of that as a series of 3 steps where I take Z and first I apply V transpose, which is a rotation. So this is rotating our coordinate system so that the eigenvectors in the directions in which I want to shrink or stretch things are now aligned with the coordinate system. And then we apply lambda, which is a matrix that stretches along some coordinate axes and shrinks along other coordinate axes. And then we finally apply V, which reverses the rotation that we did before and moves us back into the original coordinate system. So that's how I like to think of the eigendecomposition in terms of what it actually does when you apply it to a vector. And so now that we've chosen our eigenvectors and eigenvalues, or in other words, we've chosen our ellipsoid axes and our ellipsoid radii, then getting those axes and radii is just, you take the quadratic form of a to the minus 2. So how do I get those specified axes and radii? I take this isocontour of this function. This is two different ways of writing the same function, by the way. So this and this are equivalent. So this completes our task where we wanted to specify a paraboloid whose isosurfaces are ellipsoids with specified axes and radii. That's how you do it. Any questions about that?
Yeah, there are some questions. So in the beginning, someone asked if you can clarify whether this assumes that your matrix A is symmetric.
Well, so we're not starting with the matrix A this time. We're starting with eigenvectors and eigenvalues. Now, the procedure I've just described, where you take a set of eigenvectors and eigenvalues and you get a matrix A, is always going to give you a symmetric matrix, because you can see that this V lambda V transpose is inherently symmetric, because lambda itself is symmetric. You put a V in front and a V transpose at the end, it's still symmetric. So this method will only generate a symmetric matrix once you've specified certain eigenvalues and eigenvectors. Other questions?
Yeah, let's see. So someone is asking if you can repeat like what the reason is for having that V transpose to rotate the vector Z if the diagonal matrix is axis aligned.
Well, I guess I'm not completely sure what the question is, but maybe if I draw this, it will be a little more clear. So you have,
I think the question might be like what exactly the matrix V transpose is doing to your vector Z, if you can visualize that. Is that what you're asking, Lucas? Yeah.
well, the way I'm thinking of this is you start with a vector Z, and then what V does is it basically rotates that vector Z, or in this case, V transpose T, rotates that vector Z. And then we apply the axis aligned stretching and shrinking when we apply lambda. So what that means is that we divide this into components, and each component gets shrunk or stretched separately according to the corresponding eigenvalues. So maybe the vertical component gets stretched and the horizontal component, in this case, stays the same, eigenvalue 1. So that gives us lambda V transpose Z. And then the very last step would be rotating back by applying V, which undoes the original rotation. And that gives us V lambda V transpose Z, which is equal to AZ. So I think of it as 3 steps: rotate, stretch along the coordinate axes, rotate back. By the way, I see a few questions about this. So just a reminder, a rotation is any V, any orthonormal matrix whose determinant is 1. A reflection is one whose determinant is -1. And those are the only 2 choices. And someone says, isn't reflection just rotation by 180 degrees? No, it's not. You actually, if you have a d-dimensional object in a d-dimensional space, there is no rotation that will give you a reflection. Other questions, Kevin?
Let's see. Yeah, there was one thing that I wasn't actually sure about. So for an indefinite matrix, it can have positive and negative eigenvalues. Is it possible for it to have 0 eigenvalues too?
Yeah, this An indefinite matrix can have 0 eigenvalues. The definition of indefinite is just that it has at least one negative one and at least one positive one.
Okay.
If it has no negative ones, it's positive semi-definite. If it has no positive ones, it's negative semi-definite. Indefinite means neither of those two situations.
Okay, sounds good. I think that's it for now. I'll answer the other ones.
So something I want to point out here is that once you have the eigendecomposition of A, what happens when you square it? Well, you get V lambda V transpose, V lambda V transpose, but notice that V transpose V is I, so that cancels, they cancel each other out, and you're left with V lambda squared V transpose. This is another way to see that when you square a matrix, you are squaring its eigenvalues without changing its eigenvectors. So the eigendecomposition of A has exactly the same eigenvectors as, sorry, the eigendecomposition of A squared has exactly the same eigenvectors as the eigendecomposition of A. The only thing that's changed is that the eigenvalues have gone from lambda to lambda squared. Reaffirming what we already saw earlier. And we can likewise show that if you do an inverse, then you're going to be, what you're going to get is the inverse of the same eigenvectors, but now we're taking the eigenvalues to the power of -2 in this example here. Now, this leads us to a way of taking a symmetric square root of a symmetric real matrix. So if it's positive semi-definite, if it's indefinite, it generally doesn't have a square root. But if you have a symmetric positive semi-definite matrix, like for instance, the covariance matrix of the normal distribution, then we can find a symmetric square root by taking the eigendecomposition. And that square root, written sigma to the 1/2, is found in the following way. First, you compute the eigendecomposition. So we get the eigenvectors and eigenvalues of sigma. You take the square roots of sigma's eigenvalues, and then you reassemble the matrix, let's call it A, that has the same eigenvectors, but now we've taken the square roots of the we've replaced the eigenvalues with the square roots of the eigenvalues. And that gives us a square root of sigma in this case. I should say though that by far the hardest part of this square root algorithm is the first step. Computing eigenvectors and eigenvalues of a symmetric matrix is a hard topic to do efficiently, and it's not definitely out of scope for this class. But you might learn about it in a graduate math class. So now I want to come back to anisotropic Gaussians. So let's revisit the multivariate normal distribution. But now we're going to allow different variances along different directions. So we're going to call this, we're going to label this as a random variable x, which is a vector from a normal distribution with mean mu, and now it has a covariance matrix sigma, capital sigma. So here x and mu are d vectors, and X is a random variable with mean mu. Sigma is in d-dimensional feature space, it's a d by d matrix. And the PDF for this distribution is 1 over square root of, we're going to take 2 pi to the power of d, and then we're going to take the determinant of our matrix sigma, our covariance matrix, and we multiply this all by e to this complicated looking thing, which is quadratic in X, but now it's not isotropic anymore. It's ellipsoidal. And this matrix sigma, again, is expected to be symmetric positive definite, and it's called the covariance matrix. Its inverse has a name too. And since sigma is symmetric positive definite, so is sigma inverse. Sigma inverse is often called the precision matrix. Now, what I want to do is, since this thing here is kind of complicated, I want to break it down into 2 functions. So let's write f of x as n of q of x. And here the idea is that the q is the quadratic part, not including the 1/2, just x minus mu transpose, precision matrix, x minus mu. And then the n is going to be the rest of this. But that's a scalar map. That's a mapping a real number to another real number. There's no vectors anymore. The vector part is all handled by q of x, which takes a vector and reduces it down to a quadratic scalar. And it's a quadratic form, you'll notice. It's the quadratic form of sigma to the -1. So again, this n is just a scalar mapping, albeit it's where the exponential is, so that's kind of ugly. The q is where the vector stuff happens, so we're mapping a vector to a scalar, but this function is quadratic, so we've just spent this whole lecture understanding this quadratic equation and what its, or expression, and what its isocontours look like. So Q is something we understand now. It's just a quadratic bowl centered at the mean mu, and it is the quadratic form of this precision matrix sigma inverse. The other function, n, the important thing to understand about n is it's not going to change the isosurfaces. It will change the iso values, but it won't change the shape of the isosurfaces. So everything we've learned about the ellipsoidal shape of these isosurfaces will apply to the whole thing as well. So there's a little principle here, which I just stated, but I'll say it again a little more slowly. If you're given a monotonic function n from reals to reals, then the isosurfaces of n of q of x are the same as the isosurfaces of q of x. It's just the iso values that change. So the same isosurface will have different iso values before and after. So let's visualize this. So what we've got here on the left is the function q of x that I was just talking about. This is the quadratic bowl function. And so it's easy. We know how to understand this now. It's just a quadratic with anisotropic contours, but everything about this lecture has told us how to understand what these contours look like, what their radii are, what their axes are. And that's not going to change when we go to understanding the PDF of the normal distribution. What does change again is the ISO values associated with those ellipsoids and how they're relatively spaced, I guess, is one way to put it. And so these two diagrams on the left are both the same function. They're both showing you the function Q, either a 3D plot on top or a contour plot on the bottom. And then what we're doing is we're taking this function and we're running it through this other function n, which as you can see is a pretty simple function. It's just mapping reals to reals. It's convex. It curves downward, exponential shrinkage in the limit to infinity. And that is now mapping that to the normal PDF. And one thing you'll notice is that the minimum of the paraboloid becomes the maximum of the anisotropic normal distribution PDF. But the isocontours, again, are the same on the right as they are on the left. So that helps you understand the geometry of these things. So the last thing I want to talk about now is we have this thing here called a covariance matrix. Sigma is the covariance matrix. What is covariance? Well, you've already encountered covariance, I think, in the homeworks, but let's revisit that a little bit. So consider R and S as two random variables, and these could be vectors or they could be scalars. I'm going to use both definitions right away, so try to keep this dual property in mind that maybe they're column vectors, or maybe they're just scalars. And so the covariance of R and S is defined to be, and here's a vector definition. You take your random vector R minus the expected value of R. You take your random vector S minus the expected value of S. You multiply them together, and that's a transpose there. So that's another one of those outer product matrices. Of course, if R and S are scalars, then this transpose is kind of irrelevant, but it doesn't hurt. And so another way to write this covariance is that it's the expected value of this outer product matrix, R S transpose, minus the mean for random variable mu times the mean of random variable S transpose. Now that we've defined the covariance, the variance is a special case of the covariance. The variance of R is the covariance of R with itself. And if R is a vector, then its covariance is called the covariance matrix. And that's defined, well, we've already defined it, but it's easy to show that the variance of R, as I have just defined it, gives you a matrix in which you've got all these scalar variances inside it. So on the diagonal, we have the variance of R1, the variance of R2, and so on up to the variance of RD. And then off diagonal, we've got all the covariances. So by the way, the covariance of R1, R2, and the covariance of R2, R1 are equal to each other. So this is a symmetric matrix. And here, inside the matrix, each of these R1, R2, RD, so forth, are scalars, and each of these variances and covariances, those are all scalars. It's just R itself is a vector, and its variance is a matrix. Now, for a Gaussian, so let's suppose we have a random variable R chosen from the general multivariate normal distribution with mean mu and covariance matrix sigma. It is possible to show that if you compute this variance of R, or the covariance of R with itself, that turns out to be sigma. Now, showing this is not easy. You have to integrate the expectation in these anisotropic spherical coordinates, use the right Jacobian transformation. It's a painful integral to compute, but the solution comes out to be extremely simple. An important point here is that statisticians just didn't arbitrarily decide, oh, we're going to call sigma the covariance matrix. We're like, oh, we're going to call this the covariance matrix. No, it's actually, they discovered that if you find the covariance of the normal distribution by integration, it turns out that the covariance is this matrix. And so that's a happy fact. It's a kind of elegant that it turns out that nicely. A few last minute facts about the covariance before we go. If Ri and Rj are two independent random variables, then that implies that the covariance between them is 0. Now, the reverse implication is not generally true. Just because two variables have a covariance of 0 doesn't mean they're independent. But if they're two variables or two scalars in a multivariate normal distribution, then they are. So if there are two variables in the multivariate normal distribution and their covariance is 0, then they are independent of each other. And that's kind of by definition of a normal distribution. That's part of what a normal distribution is. Also, if all of the features R1, R2, so on up to RD are all independent of each other, all pairwise independent, then the covariance matrix is diagonal. The reverse, again, is not generally true. For arbitrary random variables, just because they have a diagonal covariance matrix doesn't imply that they're all pairwise independent. But if they're all variables in a joint normal distribution, then they are independent. I'm using joint normal as just a short way of saying multivariate normal distribution. So that statement is equivalent to the Gaussian itself being axis aligned. And if that happens, then we can read the squares of the ellipsoid radii off of the diagonal of the covariance matrix. And if that happens, it's also possible to show that the multivariate PDF has a special form. When you have a diagonal covariance matrix, then the multivariate is just a product of a bunch of univariate Gaussians, one for each variable. So again, on the left, we have the multivariate PDF for a vector x. And on the right, we have univariate Gaussians for each entry in X, where X is a sample point taken from this distribution R. So when the features are independent of each other, you can write the multivariate Gaussian PDF as a product of univariate Gaussian PDFs. And when they aren't, you can do a change of coordinates to the eigenvector coordinate system. And in that coordinate system, then you can write f of x as a product of univariate Gaussian PDFs in those eigenvector coordinates. That's it for today. Any final questions?
Yeah, there are a few questions. The first is, why do we call it SPD if positive definite matrices are always symmetric?
Well, I mean, it's kind of a question of semantics, whether positive definite matrices are always symmetric. So I added a symmetric in front just to be totally clear about that. I think there surely must be someone somewhere in the math literature who's used positive definite as a term applied to non-symmetric matrices, but it's not common. Other questions?
Let's see. Yeah, there was one question about what the difference is between your notation for var r versus sigma. So I think the confusion is um, if we explicitly define sigma to be the covariance matrix, then why is it interesting that you can show that var r equals sigma? Because it seems like that would be true by definition.
Well, it's not quite true by definition. It's the definition of var r is this. And it's not at all obvious that if you take R to be a function whose PDF is this, that var R is going to turn out to be sigma. That isn't something that we made that happen. That is a property that you actually have to prove mathematically by doing an integral.
Okay, let's see. Um, I'm not sure I understand Thomas's question. Um, hmm. Are you able to see his question in the Q&A, Professor?
Yeah, he says, is this like how we can split an integral into separate integrals as long as the terms are separable? Been a while since I used the term separable, so I'm not sure I actually know what that question means. I mean, it may be that when you do the integral itself, that the easiest way to do it would be to separate it by applying the eigenvector transformation, but I'm not sure. Sorry. Anything else come up, Kevin?
Let's see. I'm in the middle of answering Eric's question, so I'll type that out. Let's see.
Okay, let's see. Someone's asking, is it true that covariance RIRJ is 0 and multivariate normal distribution if and only if f of x equals f of x1? Yes, I believe that's correct. That well, I guess we should be careful. Certainly, this implies this if it's true for every I and j. When you say if and only if, the problem with the other direction of implication is this doesn't actually explicitly, well, I guess it depends how you interpret this. If you assume that these are all Gaussian distribution PDFs, then yes. The bottom circle does imply the top square here if all of these Fs are univariate Gaussians.
Okay, and there's some questions about what exactly joint normal means.
Oh, joint normal is just a different name for the multivariate normal distribution. So when I write, you will often see it in, so you should get used to it, that joint normal distribution and multivariate normal distribution are just two different words for the same thing. Other questions?
Let's see. I think that's it. Sabrina, if your question wasn't fully answered, can you just message in the chat? I'm not sure if that makes sense to you now.
All right, well, thank you very much, everybody, for your time and attention, and have a great night.